Hey everybody, we're going to do one more example using cylindrical shells. And it's a little different than the example we started the idea with to show us a little how we can use this in a greater variety of circumstances. So the idea here, or the shape we're talking about here, is we're going to start with this enclosed area between these two graphs of f and g as described, and then we're going to rotate this around the the y-axis. So let's first get a picture of this shape and then see if we can understand how to get the volume of it. So I want to do a little bit of thinking before I draw. 9 minus x squared and 9 minus 3x should be fairly familiar shapes to us. F is a downward facing parabola with zeros at -3 and 3. And then 9 minus 3x is a line with a downward slope and an intercept at 0, 9, the same y-intercept as f. So they're both going through this point. Let's put this in. This is 0, 9. Oops. And then let's picture what these are going to look like. I'm going to have a downward facing parabola and a line going through it, and so presumably the enclosed area is going to be the area between, like this. So I need to find this other intersection point. That's easy enough to find with a quick computation. This is quick enough to see is solved by 3x equals x squared, which you can probably see has solutions of 0 and 3. We already knew about 0. That's where the two graphs intersect here. 3 is the other place when x equals 3, which happens to be where both graphs hit the x-axis. So let's draw those in. So my line is going to look like this. And then the curve, the parabola, will look not as nice, but something like this. Okay, and so that's the shape. That's the region that we start with. Now we imagine rotating this around the y-axis. So if you can imagine this thing, it's going to look like a hill from the outside, but it's hollow in the center with like a cone taken out of it when we rotate it around. I'm going to draw the other side of it, the mirror image. That looks about right, somewhere about right there. And the parabola doing the same shape in this direction here. Okay, so this is the point 30. And this is about what it should look like when we rotate it, or at least this is what the two halves, the two sort of faces, if we were to slice this thing in half. So in order to get the volume, what we want to do, I want to picture this. I'm going to use the method of cylindrical shells. You could also do this one with the washer method that we did in previous videos, but I'm going to use cylindrical shells here. They will give you the same answer, or they should, otherwise everything is a lie. So here is an approximating rectangle, right? So this is coming from the idea similar to when we developed the idea of the integral, that you chop up x into little intervals. Here's a rectangle that approximates the area between them. And I'm going to imagine rotating this thing around, and I'm going to sketch in its mirror image. Looks something like this. And when we rotate it around, what we'd be looking at is a cylinder. I've drawn the back half of the cylinder here, right? In reality, it would be a cylinder, a full cylinder like this, right? And then the idea is you would do the same thing moving over to this rectangle and then a rectangle here. And for each of these, you would do a rotate around, make a cylinder, and you'd have kind of this collection of concentric cylinders whose volume is very close to the volume of the shape we're imagining. And as we take the cylinders to be thinner and thinner, the volume gets closer and closer. So we want to get an approximating volume for the cylinder, and what we imagine doing is taking the cylinder and unrolling it, right? You slice it somewhere and you unroll it until you end up with something very close to a rectangular solid. right? So you just unroll this thing, like we said last time, if you roll up a piece of paper, when you unroll it, you get something that's rectangular, okay? So there's our picture. I want the approximate volume of this cylinder. And the way we can get this is, well, we're just going to do length times width times height. This width, for instance, if you look, is just the thickness of this thing, or the thickness of the cylinder here, which is just the thickness of this interval of x, which we call delta x. The height of this thing, right, is just going to be the difference between f and g. Looking at the picture, you see this starts at the top. The top of it is at the function f, the bottom is at g, and that's true whether we're doing an interval over here or an interval over here. So this height is going to be f of x minus g of x. Sorry, I ran out of space over there. And then finally, we need this width. If you look at the picture, the width comes from the circumference all the way around this thing, right? Well, the width is 2 pi times the radius, but the radius of this cylinder is its distance from the y-axis. The horizontal distance from the y-axis is what we can consider the radius. We just call the horizontal distance from the y-axis our x-coordinate, which means the approximate volume is just the product of these three things: 2 pi x, f minus g, delta x. In the limit, this becomes our integral from 0 to 3, 2 pi x. Let's write out f and g, 9 minus x squared minus 9 plus 3x dx, okay? And there's the integral we need to work out. Let's clean it up a little bit. I'm going to take the 2 pi out front. I have x times 3x minus x squared dx. Let's do a little more cleaning up inside, just a little bit of algebra. 3x squared minus x cubed dx. And then we'll take antiderivatives. All right, what do we get? So we'll have x cubed minus x to the 4th over 4, evaluated from 0 to 3, 2 pi, 3 cubed is 27, 3 to the 4th is 81 over 4. Let's multiply through by the 2. Let's see what we get. We'll have, let's see, 54 minus 81 halves times pi. I'll just move the pi to the back. So that's what? 108 minus 81 halves pi, or 27 halves pi. And that's it. The integral part is probably the easiest part. It's a pretty simple polynomial integral. The trickier part with these is often in the setup. So hopefully this idea is starting to be picturable in your brain. It's pretty simple geometry once you get the concept down, right? We're just making a rectangular solid out of these cylinders. Okay, that's going to do it for this one. Thanks, everybody. I will see you next time.